Thank you for being again here, and hope lunch was great. I hope you liked the little networking session with Keysight, quantum machines, and Big instruments. We're going to go now to the afternoon sessions, and we're first going to start with a talk by Professor Jens Koch, who is currently a professor in the Department of Physics at Northwestern University, and he is one of the, I guess, founding fathers / one of the co-founders of the Transmon qubit, which is today probably the qubit design that is mostly used by all these companies that have also been here. So we owe him a lot, and you can learn a lot from him, which is why he's here. And then he's going to talk about introduction modeling with SCQubits, which is a design software that they established there at Northwestern. So give it up for our speaker, and if you have any questions, you can ask.
Thank you so much, and thanks to the organizers. This has been a really wonderful workshop so far. I've already learned a lot, and I'm looking forward to more of that. If you were in the morning sessions on SCQubits over in the other room, then probably there will be a lot of redundancy, but you're of course welcome to get redundancy if you want that. And maybe I'll just take one moment to clarify one thing. So it is true that my name somehow appears in the first author position of the 2007 paper that now has lots of citations because it sort of introduced the transpon from the theory side. But I arrived there as a postdoc. I got hired by Steve Gervin, and when I arrived, a lot of the ideas of the transpon were already around. Some of the first devices had been built. So don't take me as the inventor of the transpon. It's always good to be in a great place at the right time, and that is what happened. Okay. Now that we have that out of the way, so I would like to start with just checking on, well, not checking on you, but maybe together, if my pointer wants to work. How about now? There we go. Can we just together maybe sort of collect the things that you remember about the transpon, and you can just blurt things into the room. You can tell me that it's like a harmonic oscillator or how it's different. Like what do you remember? And we will start from there. It's like a harmonic oscillator. It has a little bit atomicity, right? So it's important that the lowest two energy levels are not exactly equal to the splitting between the next two. Otherwise, it would be very difficult to operate as a qubit. And anything else you remember?
Josephson junction.
It needs a Josephson junction. That's exactly how it gets its atomicity. That's right. Anything else?
Capacitor.
There's a capacitor. That's right. Okay, great. So I think I'll take that as a starting point, and we will remember some of the other things together. I did want to point out, and I think Michel Devoret already did this yesterday, but I'll do it once more. If you like classical mechanics and sort of the fact that classical mechanical systems can be quantized and can exhibit quantum behavior, then really what this transpon Hamiltonian is it's completely analogous to a classical rotor Hamiltonian. So what you see here, right, is sort of there's a stiff rod, there's a mass at the end, and it can rotate all the way around. P phi is our momentum conjugate to the angle variable phi, right? This one just checks what is the angle between the vertical and the rotor currently. And so you see that the form of the Hamiltonian, all the letters look different. That's fine, right? The P phi is called Q down here. The mass is somehow related to the capacitance in the transpon, but the form of the Hamiltonian is the same. There's a cosine phi, which comes from the potential energy. And there's a kinetic energy term, which for the transpon is actually the classical charging energy. You see this is, in fact, just the expression that you would write down for the energy stored on a capacitor with capacitance C if I place an electric charge plus minus Q on the two plates. Okay? And so if that is all so, then, I did have fun animating this at some point. So classically, right, I think Michel may have mentioned this as well. Classically, there are different types of trajectories. So if I give this classical rotor a relatively low energy below the top of the cosine, then this will look very much like just a pendulum and swing back and forth at a constant energy, convert energy between potential and kinetic energy periodically. And if I give it more energy, so now I'm above the cosine top, then it actually can just go round and round, right? Very simple classical dynamics. Okay, and now we're supposed to somehow imagine what does all of this mean quantum mechanics? Well, quantum mechanically, we don't have actual trajectories, right? There's not a fixed position. There's also not a specific momentum. There's fuzziness all around, and we say we have certain wave functions that describe the probability amplitude by which we will find this particle in certain positions. And so if you look at the ground state energy, the ground state energy is here, and if you look at the corresponding ground state, this is its wave function. It's very close to a Gaussian because it's close to a harmonic oscillator. You know that. And so if I try to express this fuzziness that is encoded in the wave function, then, well, this is a little bit what it looks like, that the particle is smeared out over that range. And I'll maybe make one comment, which we'll see what your reaction to that is. People love to talk about 0-point fluctuations, and they will say, oh, you know, this fluctuates. And my response to that is, well, actually, as long as you don't do anything, there's nothing that's fluctuating. This is the ground state. It's constant. The only thing it does as you time evolve it gets a dynamical phase factor, and that's it. The only thing that looks like something is fluctuating is if you go in and start measuring and asking, well, where is the particle? But you have to realize, and I'll comment on that later again, that measurements in quantum mechanics are not the innocent thing that they're in classical physics, right? You actually change the state when you perform a measurement. That's this comment. Okay, so this is a typical wave function that we would see in a transmon, and we'll briefly, I hope, talk about other kinds of states. So here's one that is sort of reminiscent of the rotor going round and round and round, where the particle is almost equally likely to be found anywhere if you perform the measurement. And historically, those states they were realized in a much older version of what is now called the transmon qubit. What Michel didn't, I think, comment on was he in many ways, he invented the transmon in 1998, just in a different parameter regime. But it's the same circuit, and I'll talk a little bit about that because it'll also allow us to talk a bit about noise, how much have you learned already about noise? I was hanging out in the other room a lot. Have you talked about T1 and T5, T1, T2? Just a little bit? All right, good. So we'll talk about it. Great. Because really, when it comes to building qubits, we should ask ourselves, why are we so slow? Like it was 1992 maybe that Peter Shor published a paper that said, look, build a quantum computer, build something out of qubits, and it'll be much faster at certain tasks at least than our classical computer. Why is this taking so long? And the truth is that what qubits have to do, or what you have to do as you try to build good qubits, is you have to find a compromise. And the compromise has to do with the fact that no qubit is alone in the world, and every qubit to some extent talks to its environment. It listens to its environment. There's noise in the environment, and you couple to it. I can sort of phrase this in more formal language, but there's unwanted interactions with the environment. And what that does to a qubit is typically it leads to the qubit starting to behave more and more classic. Okay, and that's not what we want. So on one hand, we try very, very hard to isolate the qubit from all these noise sources as much as we can, because that makes them longer lived. We'll talk about T1 in a couple of slides. So its quantumness will be improved if it's isolated. Now, there are certain things in this world which are fantastically isolated. You've heard of neutrinos, I suppose. You've also heard of the fact that as they come from the sun to the earth, they actually coherently change their flavor, right? They're fantastically coherent, but they're terrible qubits because they sort of fail on the other end of this compromise, where a qubit is only a good qubit to us if we at least can talk to the qubit. Right? If the qubit doesn't listen to us, if we can't manipulate its quantum state, if the qubit can't be read out, then well, that's a useless qubit. So neutrinos are very well protected from the environment because they don't interact very strongly with much of anything. But we need our qubits to interact at least with us and the control circuitry that we build to manipulate its state and read it out. So that's the compromise we have to establish. Okay, and so if we talk about this a little bit more formally, then this would go under the name of decoherence. This terminology is there's some differences in the literature. The way I use decoherence is I use decoherence as the umbrella term for everything that destroys quantumness. And I distinguish in a little bit more detail between well, relaxation is sort of the narrower part of depolarization. I'll explain it in a moment, and pure dephasing. And so we'll talk about the difference between those and what it all means. Good. So here's our qubit. I'm drawing it as a circle with two levels. You know by now that actually no superconducting qubit has just two levels. That there are always higher levels. We actually have to be a bit careful about that too. But for now, my symbol is going to be as simple as that. And here's an arbitrary single qubit state, some superposition of 0 and 1. And so this qubit sits on its chip. And we are actually aware of a whole bunch of channels of noise that affect the qubit, or can affect the qubit, depending on what precise qubit it is. We know that there's something called 1/f charge noise. There's flux noise. There's critical current noise. There's dielectric loss. There's photon shot noise. There are non-equilibrium quasi-particles. And in some ways, I could spend a lot of time trying to explain what all of these are. But if you look at least most of them, the first 4 to some degree, if you look at those very carefully, you will discover that even if I spend an hour talking about them, our microscopic understanding of these noise channels is relatively limited. You will hear people very quickly blame two-level systems. And if you ask them, well, what is that two-level system? They will say, I'm not so sure. That they could be vacancies, they could be whatever dirt is around, and it gets very fuzzy, okay? So the microscopic understanding of all these noises is somewhat lacking. And if you're really smart and really ambitious, then one thing you can try is to not just to figure out what they are, but in fact, how do you actually make the noise a little bit less noisy, right? That would be something fantastic that everybody would benefit from, but that seems to be quite hard. Okay, and so the qubit sits there and it's exposed to all of this noise, and that noise causes loss of quantumness or decoherence. And in a quantum computer, it leads to errors unless you do something about them. And so I think I keep joking that if your quantum computer were running some Windows operating system, would constantly show you a blue screen of death message that said your qubit ran into a problem that it couldn't handle it now and needs to restart. And that's bad, of course. There's a question.
Question online. What is critical current noise? When does it become the dominant noise source?
Okay, so critical current noise is perhaps one of the least studied noises in superconducting qubits, in part because it is not the dominant noise channel anywhere close to so far. I would even, off the top of my head, I actually don't know the exact level at which it would become so the hand wavy picture of what it is you have a Josephson junction, and you've sort of seen both theorists and experimentalists get up here and show you slides, and the slides look very different in nature, where sometimes people draw what I as a theorist would love to draw, which is a very pristine, clean, plain surface, which is your lower piece of superconductor, and then you draw a very pristine and clean and plain surface of oxide on top, and then you draw another piece of superconductor there, and everything is like very geometric and that's nice, right? That's not really how Josephson junctions look like. I think one of the speakers actually had this wonderfully ugly image of a Josephson junction that Luigi Frunzio took a long time ago. And if you looked at it, I think, I forget whether it was Slatko, somebody even commented on, the speaker even commented on, all this little dirt stuff that is around you, you can ignore, and it's all very simple. But the fact is, it is a magnificently ugly thing. And if you ask sort of from the perspective of microscopically what's going on, is this really a plane interface where tunneling of Cooper pairs is equally likely in all places? Yeah, no, that's not the right picture. This is a very rough surface. There may be places where there's a little indent on the top and a little dimple on the bottom, and that's predominantly where tunneling will take place. And if there's any spatial rearrangements of atoms in this junction, then tunneling is exponentially sensitive to this distance. So if you have any such thing, then you might get fluctuations of the critical current. Okay. Good. But fortunately, and I think nobody I've talked to has ever given any idea of actually what to do about that kind of noise. But fortunately, it's very much subdominant and doesn't bother us so far. Good. So now let's distinguish these roughly two types of decoherence. There's one thing that in the downwards direction, we'll always call it relaxation. If we include upwards transitions, perhaps because there's an elevated temperature, then a relaxation is an awkward word, and people call it depolarization. So what is happening? Suppose we start our qubit actually in the excited state. That's my little blob up there. And the coupling to the environment might allow the qubit to emit that excitation into something in the environment. Maybe it falls down and emits a photon, maybe it's a phonon, whatever the bath is, we don't care. Spontaneously, the qubit loses its excitation, and so whatever the superposition before might have been afterwards is now in state 0. That's an error. That's a T1 process, and T1, in fact, is the time scale at which this process takes place. Okay, average time scale. Good. And so in principle, I could talk a lot more about these T1 times. We have some ways to try and estimate them and compute them. I can maybe say just briefly, there are two important ingredients for this. There's a matrix element that says I can go from 1 to 0 by means of a coupling operator A by which the qubit sees and talks to its environment, whatever that is. I've kept it a symbol. That's one important ingredient. The other important ingredient is, well, what does the environment look like? So there's a noise spectral density, that's this function S of omega, and that gets evaluated at omega q, which basically asks at the qubit frequency, how noisy does the bath look? Okay, so that's T1. And then, okay, I already talked briefly about this. I can perhaps briefly mention that there are different kinds of baths. The simplest and somewhat pathological, but simple bath is a bath with white noise, where the noise power spectrum is just flat. There's no frequency variation. Other types of noise that we encounter do vary with frequency. So 1/f noise, by its name, has this behavior. This is a log scale, so it's a linear function on that. But there are other types of noise, and in fact, when experimentalists very carefully measure whether they see 1/f noise, it's not always so clear that it's strictly 1/f. Sometimes the exponent looks a little bit different. Okay. Now, the other thing I mentioned, there's another type of decoherence, and I would like to, everybody would like to distinguish it from depolarization. Depolarization went along with emitting an excitation into the bath, where the reverse process is gobbling up an excitation from the bath at this finite temperature, right? Now, this process, where we talk about purity phasing, does not require any energy exchange with the bath. So the simple picture there is, you have your qubit here, and well, it has a certain energy splitting. You even saw a little bit for the transplant what that energy splitting looks like in terms of EJ and C. But now suppose that the qubit couples to its environment in a way that slowly but surely and randomly varies this energy splitting, right? So I'll do it again. It's supposed to be random. I'm doing a bad job with my poor animation, but you can imagine some random fluctuations of this energy splitting. And now if you remember just a little tidbit of basic quantum mechanics, the 0 and 1, right? They're eigenstates of the Hamiltonian. And so if this is my state at time 0 and I ask, well, how do I evolve forward in time? Then eigenstates of the Hamiltonian are super simple, right? They're not complicated. All they get is this dynamical phase factor. And here I've basically chosen to shift my energy spectrum so that the energy of state 0 is set to 0. That's my reference point, which means the only dynamical phase factor that I get to see is this one here. And this one is now the energy difference between 1 and 0. So eigenenergy 1 minus eigenenergy 0. That's exactly that difference, okay? So here we have this dynamical phase factor, this energy splitting enters. And so if I now imagine that this energy splitting randomly varies, then, well, this is a somewhat awkward way to express this, but at least intuitively, this is what it is. This thing becomes randomized, and I cannot keep proper track of my phase factor anymore. And if you think that that is harmless, then we're back to classical computing, right? Because these phases are incredibly important for quantum computing. We need to, like that is what we play with. And so there is a way to make this more formal. If you've never seen the density matrix, then this will look a little bit like gibberish, but if you've made contact with the density matrix, then the simple message is under pure dephasing, what happens is that the off-diagonal elements of the density matrix that track that there's actually a pure state and the superposition of the basis states, those go away. And that means you're just left with a statistical mixture. So in some ways, quantum mechanics indeed has gone away. Okay. And when we asked about, well, can we at least motivate, I'm not going to derive this expression, but can we motivate it? That's also not so hard. So the inverse timescale for this pure dephasing checks how much our, okay, I'm calling it omega q, how much my qubit splitting varies with whatever fluctuating parameter is causing this variation. And so this is just the first derivative of the energy splitting with respect to the fluctuating parameter. That's basically this, how sensitive is my qubit splitting with respect to this bad noisy parameter. And then different from depolarization, here, since there's no exchange of energy with the bath, it turns out that the noise spectral density actually gets evaluated at frequency 0. Now, if you are paying good attention, then you should yell at me and say, well, how is this supposed to work if it's 1 over f noise? Because 1 over f means like 1 over omega, and so if I plug in 0, well what's going to take place? And so I'm glossing over details here. There is a way to extend this expression for 1 over f noise. Strictly speaking, 1 over f noise also actually needs cutoff somewhere. Otherwise, it doesn't, like there's a divergence eventually. But so for simplicity, we will just keep in mind that this expression cannot be directly used for 1 over f noise, but it signals that 1 over f noise is particularly bad for pure dephasing. Okay. Any questions so far? Anyone? All right. Good. So what do we do about all this noise? I said, well, if you're really ambitious and want to do something really cool, then find a way to actually reduce the noise. Like it has a certain volume today. If you can make the noise a bit quieter, everybody will love it. Okay, but that appears to be a pretty hard problem, and definitely as a theorist, I don't have much to contribute because that has very much to do with material science and fabrication, to some degree, maybe microwave engineering, but that's hard. So what have people done instead? We've played this game. We say, well, we understand that there's noise. And so what we'll do is we'll basically make the qubit deaf with respect to the worst noise sources. Okay, And that's a game you can play even without diminishing the volume of the noise itself. You've gone to places that were loud. You put in earplugs and you feel happy, and then the qubit will feel happy, right? And then the place where the whole field, of course, is going is this game is useful and can be played for a while, but ultimately we know that this is not going to be enough. And ultimately we need active quantum error correction, which really is a bit like your noise canceling headphones, where you monitor what's actually going on the outside, and depending on that, you do perform a certain operation, in this case on your qubit, that is supposed to correct.
Now we have 3 questions.
Yeah.
So the first one is, what was the factor that we discussed about randomness being bad for periodic phasing?
The factor. Okay.
Before.
Yeah. So this was, let me back here.
Yeah.
Yeah. So this is I call this the dynamical phase factor. I think many people do. I don't know whether there's other nomenclature. But so just keep in mind that the states labeled 0 and 1 here, sorry, are actually eigenstates of the Hamiltonian, right? And those are very special because they don't change their shape. They don't, under time evolution, they don't make a transit from one state to another. They just stay where they are. That's why I said earlier that eigenstates of the Hamiltonian don't fluctuate. And all they get is a boring dynamical phase factor.
Next question, why are we only considering relaxation? Couldn't the qubit also absorb energy from the bath and go from ground to excited?
Absolutely. I meant to say that, but I may not have been clear enough. So as soon as the temperature of the bath is not 0 temperature, which basically is any good old bath, there is a chance that we will find an excitation, we'll find a quantum of energy that is good enough to get the qubit from the ground state to the first excited state. And that is exactly why talking about T1 as relaxation is not exactly enough. That's why there's this term depolarization, which includes both excitation and relaxation.
And then finally, what is the physical origin of the noise? In NMR, 1 over T1 is related to the noise in the transverse magnetic field, and 1 over T5 is the longitudinal part. In transmon superconducting qubits, what replaces the magnetic field?
Okay, so in a flux tunable transmon, definitely away from certain operating points that are more stable, it would be flux noise that might be the limiting factor for purity phasing. For T1, it's usually dielectric loss, I guess, that is identified as the culprit for allowing excitations to enter and exit. Is there a question? No? All right. Okay. Good. Okay. And so here comes the little historical part where I want to tell you that in many ways the transmon qubit is a very old circuit. And we've basically played exactly this game here to address one of the most detrimental channels of noise that the original circuit experienced. And that was 1 over charge noise. So we'll talk about this. So if you go back in history, potentially to a place where you weren't born yet, I don't know. But I was born, so I can talk about it. 1998, 1999, there are 2 very beautiful papers, one that involved Michel Dubouré and one Yasu Nakamura, and they almost at the same time produced a circuit that you might recognize. It looks like this. It has a superconducting island here, and then over here, I'm sorry, my thumbs appear to be too big. Okay, so superconducting island over here. This thing is a Josephson junction. So through this barrier, qubit pairs may hop to the other superconductor, which basically is connected to ground. So this is supposed to be a big reservoir of qubit pairs. And then ground is also connected via a gate voltage to a capacitor. Here's one of the capacitor plates. The other plate is basically this face of our superconducting island. And this was originally called the Cooper. Well, actually, Cooper pair box is how it really entered into the literature. Here it's called Cooper box. All right. This circuit is essentially identical to what you saw as the transmon. Maybe in this form it doesn't quite look that way, but keep in mind that this symbol here, the X with a square around, is actually just an abbreviation for a pure Josephson junction in parallel with a capacitor. That's what that symbol always means. If you somehow manage to make a Josephson junction that doesn't have a capacitance, then you would just do the X. If it has a parallel capacitance, which usually we have, you make the box around. And so for the transmon, you have this box. Sometimes we also draw yet another capacitor in parallel because we want that capacitance to be bigger. But here, you would just draw the single box. Was there a question? No. Okay. Good. Now that circuit, believe it or not, was so short-lived that the biggest credit that I give that to experimentalists, and it's not just credit, I admire that, is that there's a certain stubbornness in looking at this figure and saying, let's go and continue, right? Because this nanosecond, well, it sounds short, but why is it short? Well, this is the dephasing time. So this is for how long the circuit behaved properly quantum mechanical, so to speak. And I should compare that with the time scale needed to do anything useful with that circuit, including changing its state and reading it out. And everything there takes at least as long, but actually longer, right? So this was a very short-lived qubit. And I don't know. I might have given up. I would have been a bad experimentalist. So, but people kept going, and in fact, historically, some of the things that happened next was what people discovered and understood better and better that what this circuit is limited by is this 1/f charge noise. What is it? Well, we actually don't know. Again, microscopically, we don't know exactly what it is. But the hand wavy picture is the following. What you're trying to do is you try to establish and control the electric potential on this plate via a gate voltage. Okay, and it turns out that nature does its own thing. Perhaps there are charged impurities around that wiggle, that change their positions. I really don't know, but something is adding a component to the electric potential that fluctuates, and it follows a 1/f spectrum. And that is precisely what was behind this short dephasing time. And so at first, people turned to other kinds of circuits. People invented phase qubits. People invented flux qubits. Flux qubits actually held some of the world records in T1 for a good long time. And then only in, I don't know, 2006 or so, Rob Shelcup and Michel de Louvet started talking and decided, well, this old circuit, the Cooper pair box, maybe we can use it in a different parameter regime. And so what is actually happening? This 1/f charge noise can be rephrased as what we call the offset charge. You've heard it yesterday several times. It enters the transmon Hamiltonian, but it really just encodes this this gate voltage along with whatever nature is doing and letting it fluctuate. And so if you look at the energy levels of the original Cooper pair box, then this is the situation. So you have a lowest lying energy level, and I'm plotting this as a function of this offset charge parameter. Ideally, what we want to happen is we choose the offset charge, perhaps here, right? And we would like it to stick there. And then this is our qubit energy splitting. The next higher splitting would be this one, because this is level 0, this is level 1, this is level 2. All right. But you can tell if this is what I see for the offset charge instead of just a constant bias, then, well, what will happen is that this working point will wiggle around, right? I tried to animate this again in a somewhat poor fashion, But you can tell that as this working point varies to the left and right, the qubit energy is varying, right? And we saw that that is precisely what leads to dephasing. That's why the Cooper pair box was so short-lived as far as dephasing was concerned. Okay, and so now we look at our Hamiltonian, which in fact, this Hamiltonian is both the Hamiltonian of the Cooper pair box and the transform. The only thing that's different between those two things is, well, basically the only thing that you can vary. So as a theorist, I look at this Hamiltonian and I see there's two energy scales. And I can choose to express one in units of the other. So there's only one dimensionless parameter that I actually get to vary, right? Now, there's an overall energy scale, which is important. Like if you ask, can I just make my qubit very low energetic? That may have some advantages, but also disadvantages. But so to distinguish between transmon and Cooper pair box, all we need to discuss is what is the ratio between the Josephson energy and the charging. And well, I've made a couple of plots for you, and we will actually make a couple of plots together in a few moments when we look at the SCQubits package. But here they are. So this is again energy levels 0, 1, and 2 as a function of the offset charge. And what varies from this panel to this one. Wait, my thumbs must be growing. Come back to me. All right. So all that is changing from the left to the middle to the rightmost panel is the ratio of EJ over EC. Right? Here it is low. Here it is somewhere in between. And here it is large. This is the transmon regime. This is the Cooper pair box regime. Okay, and you can tell what the difference is. Here we see, well, if the offset charge wiggles, then all my qubit energy splittings will wiggle. Here that is slightly reduced, and here it looks like almost nothing is changing anymore. Right? So the whole purpose of taking the Cooper pair box from this original charging regime to the transmon regime is to make these energy levels flat with respect to offset charge, because offset charge is the worst culprit in producing dephasing in that device. Okay. Any questions about that? Yes.
So when you change the transmon regime, what changes in your system that makes it, say, maybe perform better or worse in that regime? Like, is there something that's faster or slower?
Well, I mean, the best way I have to explain why performance is better is to point at the flatness of energy level.
Sure. So I imagine that there was no noise, just for
no noise.
Yeah. So imagine it was perfect. There was no 1 over f noise.
Mm-hmm.
What would be an advantage or disadvantage between working in the charging transmon regime, right? Because there's only 2 parameters here. Your potential's up, your kinetics higher. Like,
yeah. So, I mean, if there were absolutely no noise, then you can work wherever you want.
And it wouldn't affect, like, say, gate time performance or anything like that?
Well, you might be able to do, in principle, to do gates a little bit more quickly here because the anarmonicity is bigger.
Yeah.
But it's not really comparing apples and oranges because the way operations are done are actually quite different in the transmon as compared to the Cooper pair box. In the Cooper pair box, it's done with this gating, and the states here actually have a very simple interpretation. So this state here, for instance, as I follow it up the parabola, is nearly a charge eigenstate. So in the Cooper pair box, there's this beautiful, simple picture of your qubit 0 state is the state where the island in this device is nearly charge neutral, and say the first eigenstate is the one where you've added one single Cooper pair.
Right.
And we'll see in a moment that for the transmon, well, that's not the right picture. Those are big superpositions of lots of charge states.
So it's like a coherent state, basically, in the transformation?
Well, it's a coherent superposition of charge states,
Okay.
but it's not the kind of coherent state that you would say is generated by displacing the vacuum
I
of
see.
an oscillator.
Thank you.
Two questions. So online, what was NG again?
NG, yeah. So NG is also called the offset charge. It enters the Hamiltonian in this peculiar position. This is your kinetic energy term. This is a little bit like your momentum operator. And so it enters in a place where, well, you know, if you've never seen magnetic vector potentials and how charged particles react to magnetic fields, then perhaps you've never seen anything like it. But that is the place where in 3D for charged particle, magnetic vector potential would make its appearance. And physically speaking, it's really just encoding the presence of this gate voltage, which is modifying the charge on that island through the capacitor.
Then I actually have a question.
Yes.
For the, I guess, ratio, where would you ideally like to place it if you want to access higher energy states, but not be too sensitive? Like, would you put it at 40?
If I want to access higher energy states, so people have climbed the transmon ladder for a range of EJ over ECs.
Yeah.
I think I don't see, like, unless you make EJ over EC vastly large so that it basically you lose your anharmonicity, then I would be a little bit careful. But otherwise you have enough frequency selectivity. You can play games with you know, drag pulses and such to avoid it.
I guess follow that also online. But kind of to that is like, what's the physical implications going to higher EG ratio?
Physical implementation. Yeah. So the nature of the eigenstates change, and we'll see a little bit about that, more about that when we jump into Jupyter Notebook running SCQubits. The two important consequences as far as the energy spectrum are concerned are, number one, we saw that the energy levels get flatter. That's a good thing. That's what we want. We also mentioned the thing that is less good is that the energy splittings become more similar to each other, so we lose some of the anharmonicity. But what rescues us, really important, is the flatness of these energies relative to NG. That happens exponentially in EJ over EC, whereas the loss of anharmonicity is just a square root power law. So one thing happens very quickly. The other thing that we don't like so much happens slowly, and that's why the transmon works in a decent parameter region.
So if I understood it correctly, you were saying that the 1/f charge noise can be thought of as the offset charge noise back in the NG part?
Yeah.
So does that mean that, like, as frequency reduces, this offset charge also should increase?
The fluctuations are more pronounced at low frequencies. So
Yeah.
that means if you look at the noise trace, if you look at short times, it looks like it's not so harmful. But if you look at very long time scales, you'll see that 1/f traces kind of wander all over.
Yes. So now the frequency dependence is passed on to the charge offset.
Yes.
So in the plot you had for NG versus T, that's not the frequency time thing, right? Because here it doesn't really, I don't see any pattern.
Oh, I think
That's just
if you
something else.
wanted to see the drift, I'm pretty sure I actually generated a true to God 1/f noise trajectory. But if you wanted to see
You
like
want to
larger
see more?
deviations, you'll want to go farther out.
Okay.
Yeah.
Thank you.
All right, good. So how are we doing on time? 45. So that gives us enough time to, well, I can briefly mention, if you haven't heard of it yet, that beyond the transmon qubit, there are other kinds of superconducting qubits. They, again, for historical reasons, all get funny names. You know, don't pay too much attention to that, but you already know this one. This is called the transmon qubit. There's one that you that you can make from a transmon, at least on paper, by just adding a single inductance in parallel. And what that does is, you remember that this cosine here is actually the potential energy of our qubit. Once you add an inductor in parallel, you get a parabolic background. And so these devices, the transmon qubit, fluxonium qubit, look quite different. They behave quite differently. One of them has periodic boundary conditions, one of them doesn't. And I'll show you how with this open source package that we published called SCQubits, it's very easy for you to play with these qubits, learn about their properties in a very simple way, basically without doing any coding. Okay, so I'll skip over a bunch of things. This is just talking about SCQubits. If you followed the install instructions that were shared, then SCQubits was a dependency of some other package and was installed automatically, I believe. And so now I'm going to mute you for a little bit and we'll play with the graphical user interface. For that, I have to jump into it. Is this visible? Okay, and
They're all on the Google Drive, so you have access to them. You can follow it or watch.
all right. So there's 1.5 lines of code. I need to import SCQubits. I'll abbreviate it as SCQ. That is what the first line does here. And then, okay, so now you're watching two typos, or hopefully not, but all you need to do is say SCQ.GUI, and it looks like a function, and you initialize it, and then it brings up this wonderful user interface. And so there's no more coding from here on. Well, I mean, to be honest, of course, this only represents a small fraction of the functionality of what's inside SCQubits. Like if you want to do research on devices and coupled qubits and such, this is not all there is, but it's a great starting point. And I've seen, in fact, people use it in the classroom, and it seems to work for that. So let me just describe some of the things that you can do. Number one, at the very top, you can pick whatever qubit is included in the package, and there's transmon. Tunable transmon is a variety of transmon that has 2 Josephson junctions, so you can tune the frequency of that qubit also with flux. We just mentioned fluxonium, and then there are other qubits that I'm not going to mention much, but so let's maybe stick to transmon for now. If you're unsure what the qubit is that you picked, you can actually, from main, you can click on the qubit info tab, and it will bring up the little infographics that shows you the Hamiltonian circuit, parameters, and a sample image. If you're not sure what are good parameters or what are parameters that have been studied in the literature, you can hop over to the next tab, and we're trying to extend this. This looks ancient by now, but still good parameters today. Over here are more option things, which maybe I won't dwell on much. So you see sliders where you can change ranges of sliders here. And then if we were to talk more about noise estimates, then a lot of the defaults and options for noise go here. But let's stick to the simple things for now. So what you get is an option for your chosen type of qubit. You can look at different kinds of plots. The first kind of plot is the energy spectrum as a function of whatever parameter you feel like you want to explore. Right now, it's showing us the flat energy levels as a function of offset charge. I can show you that if we diminish EJ over EC, we should start to see charge dispersion. So we should see how the energy levels vary. So let me decrease EJ, and you see that it starts at the top. If we go lower, and it comes further towards the bottom, and you see that everything starts varying with offset charge. So right now, this would rather be a Cooper pair box, not a transmon anymore. And I can take it back to larger values, and it's flat. Okay. What else? In principle, you could do things where I would have to think and see how, like, what do I expect? You could say, all right, I want to see how energies vary with EJ. That's somewhat academic because EJ, at least in a non-tunable, non-flux tunable transmon, EJ is a fabrication parameter, and once you once you fix it, you don't get to change it easily anymore. But of course, on just computationally, you can ask, well, how do energy levels vary if I were able to change EJ? Okay. The next one over here is you can start looking at wave functions. So here's a plot of the potential energy. I'm going to include a couple more states in my plot, just so that we see the top of the cosine as well. There we go. All right. And so you see that there are discrete energy levels and corresponding wave functions, both inside the cosine well and above. It's very important, like sometimes people get confused and say, you know, I understand the hydrogen atom, and if I go above the Coulomb potential, then things ionize, and actually my states, the energy spectrum up there is not discrete anymore, right? It's a scattering spectrum with a whole continuum. That does not happen for transforms. And that has everything to do with the fact that there are periodic boundary conditions in place. And so you can see what the wave functions do. Again, you can play a little bit and see, you know, what happens if I make EJ smaller. That means that I'm fixing my kinetic energy scale, which is EC. So the mass of the fictitious particle remains the same, but I make the potential shallower. And you can see that that's indeed what happens. As I make it shallower and shallower, there are more and more wave functions above the cosine well. And I'm pretty sure that if I go to the original Cooper pair box, probably everything is above the well. The well is so shallow that we're having trouble even seeing it in this plot, right? Okay. Then another thing that you get to play with, and I wonder whether you've heard a little bit about readout and drives, right? Okay, I'll connect to that in a moment. But there's a question
on the wave function. There was a question: what is end cut?
Thank you for that question. So yes, that's a very important question. So how is SCQubits actually computing anything here? It tries to be careful, and it uses the Hamiltonian that has the full cosine potential. So it doesn't do the harmonic oscillator approximation. It works with the full cosine potential. And now we could, this is a beautiful exercise, but I don't think I have enough time for it. So I'll just sort of tell you how that exercise goes. I could ask you, so given this cosine potential, imagine a particle in a cosine potential, how would you actually numerically compute eigenenergies and eigenfunctions? It turns out that there are no, well, if you want to say they're exact solutions, they're all expressed in funny special functions like mature functions, and the eigenenergies are mature characteristic values, and they all actually have to be computed numerically. So how would you go about constructing the Hamiltonian? There are different options. You could say, well, one basis in my Hilbert space that is particularly nice is the basis made up of charged states. You know, the charge state 0 is the state where I have my island is charge neutral. Then there's the plus and minus 1, where there's one additional Cooper pair or a missing Cooper pair, and so on. And so if you think carefully about that basis, then number one, that basis is, there are infinitely many orthogonal states, right? All the positive and negative integer numbers label those states. So your Hamiltonian matrix is infinite dimension, which means that unless your computer works very differently from mine, we have to truncate that matrix, right? We have to say, okay, we're going to chop off the top and the left and the right and the bottom, and we're going to focus on a little square, which goes from minus n cut to plus n cut. So that's the direct answer to wherever the question came from. There are cutoffs everywhere in SCQubits. And in fact, we have to be a little bit careful with these cutoffs, because we should check whether we've converged with respect to these cutoffs. It's pretty clear that if I make the matrix too small and I chop off too much, then I will lose accuracy. So that's something to check. Okay. All right. Now, I wanted to mention matrix elements which pop up when it comes to driving a qubit. So how do we get a transmon from the ground state into the first excited state, which are our computational 0 and 1 states? Well, I hope somebody mentioned to you before that one way to do that is to switch on a microwave drive. Perhaps it's coupled in through some resonator, but at the end you need to couple to the charge operator of the transmon, and that is what allows you to drive that transition from 0 to 1. And so, as I said, these matrix elements are very important, which is why you can inspect them in here. Let's jump over here again. So here are, this says N operator, that is the charge operator. And you see that there's a very specific pattern that these operators follow. And actually, you shouldn't be surprised that they follow this pattern, because if or when I rewrite the charge operator N, that's the N operator, in terms of harmonic oscillator ladder operators, A and A dagger, you will see that N, okay, N is charged, so I should say IA dagger minus IA. But it's basically A plus A dagger with an I up front, right? And so A and A dagger allow you to go from one level in the ladder to the next, only to the nearest neighbor, right? And that is what you see here. I can't go from 0 to 0 by the charge operator, but I can go from 0 to 1. That's a big one. I can go from 1 to 2. And from 2 to 3, and so on, right? Those are the charge matrix elements, this in fact explains why, when you do two-tone spectroscopy for a transmon, it's very easy to see and find the resonance of the 0-1 transition, but directly driving the 0-2 transition, this is where I have the point, would be very hard. There's a trick where you can drive at, what do I have to say, half the frequency. It's a 2-photon transition. So there are tricks, but directly driving that transition would be very hard. Okay, I'm nearly out of time. I'll just jump to like there's one display of matrix elements of this kind. You can also switch on sort of numerical values if you want to not just have something qualitatively and read off values. There's also a way to look at how do matrix elements behave as I change some external parameter. The other day, a good collaborator and friend asked me, can I, if I change EJ, can I ever drive the 0-2 transition? How low in EJ do I have to go? Let me make this plot a little bit less. There we go. So, and the answer is, well, as far as the matrix elements are concerned, 0-2 is so close to 0, almost all the way up to EJ equals 0, that I would expect that's a very hard transition to drive directly, even if you go away from the transmon regime. And then last but not least, and this is where I think I'll have to end in the interest of time, there is a tab here, which actually to compute something always takes a little moment. But this is the tab where we try to give an estimate of coherence times. So there are various noise channels that we know of. You see some of them listed here. And so SCQubits, using some of the defaults that are hidden here under noise parameters, tries to estimate what you would expect for coherence times when these noise channels are present. And I say estimate because most noise channels have some sort of fudge factor that really needs to be read off from experiment. So I would not claim that we can predict coherence. All right. So this is in a nutshell what this little graphical user interface can do for you. And this is where I have to end almost right at the time. And I'll take some.
Can you give an example of what you use SCQubits for in your work?
Yeah.
You mentioned there's more advanced.
Yeah. So I can jump over into a notebook that I had up in the morning.
You have access to that?
Yeah, you also have access to that. So a lot of the research that we do has to do with larger systems where we couple multiple qubits to resonators and such. And oftentimes we want to run parameter sweeps over these composite systems to maybe understand where should I position my resonators so that my AC Stark shifts are large enough and such. And so there's a lot of functionality that allows you to create multiple qubit instances. I'm setting up two flexible transmons here and an oscillator. And then there's a way to combine them in a joint Hilbert space. And finally, there's this is now a little bit more programming, but you can run a multidimensional parameter sweep over this composite system and automatically get dressed eigenenergies and states, AC start shifts if you're dispersive, things like that.
Okay, I'll do one online. Okay, maybe quick one. On this software, so SCQubit, is there a way to compare the resonances?
Compare resonances.
The right.
What can you help me understand?
I guess if you drive the system, or look at like a resonance plot.
I mean, what we do is, of course, we compute energy spectra, and those can be compared with two-tone spectroscopy if you do it right. If this is a question about simulating dynamics and time evolution, then the answer is what SCQubits does not try to do is to compete with QTIP. We don't see any reason for that. QTIP is a fantastic Python package that does quantum evolution, both for closed and open systems. What we do on the side of SCQubits is we provide helper functions that basically give you the right ingredients on the QTIP side. So if you wanted to simulate open system dynamics with MESOLVE in QTIP, that's the master equation solver, there's a helper function that gives you the right pieces that you can hand over to MESOLVE to do a simulation like that.
Personal one?
Yes, so that was a really nice talk, thank you. So I don't know if I saw correctly, but one of the available qubits is it a fluxonium?
Yes.
So how exactly do you compute that? Do you have the number of junctions you have, or how do you deal with the space being so large?
So that's right. So the model that we have for fluxonium, and so we can just test whether this is working. Right, I'll switch over to fluxonium. I don't want the noise. Maybe I want to look at wave functions, and I will switch over to qubit input. So here you see what the model inside SCQubits is for a fluxonium. It does not track the presence of array junctions, right? It uses a reduced model that says, even if you have a whole array of Josephson junctions, there's one mode of the fluxonium, which is the primary qubit mode, which we can model by classical inductance. Yeah. So you're asking, of course, an important question because array modes are important, but this would not be something, if you really wanted to simulate array modes and 50 junctions, that would not be a great thing to have in a graphical user interface because those computations will be very slow. So you would move a slider and then go drink coffee and wait for half an hour and then come back like that. That's not so entertaining.
I'll take one on like, while you were referring to the well, what does the well represent? The cosine potential well.
The well, the well is just a synonym for local minimum. That's all. That was a question.
I just wanted to ask, when you do the noise estimates, do you write somewhere what is the model that you use?
Yes, we try. I think that there may be places where, especially if you have comments, that there may be places where we need to improve. Sorry to have news pop up, but I just want to go to the online documentation. So if you go to coherence times, then phasing, right. So we try to write down exactly what our assumptions are, what we use as the default parameters, and if we're careful enough, then there should also be references back. I don't know where the references go. There used to be. Well, there's one here, but I think we need some more for dephasing. So we try to share exactly what it is that we implemented.
Yes.
Question online. Wouldn't the charge always be even since it is the charge compares?
So yeah. Certainly, so if we forget for a moment about the possible presence of quasi-particles and broken Cooper pairs, then if you count charge in electron charge rather than twice the electron charge, that would always have to be even. But the charge operator that Michelle introduced, that I use, that basically anybody in the field currently uses, counts in terms of twice the electron charge. So that number therefore can be both odd or even.
Any more questions? If not, we'll take a 5-minute break before we have a 2-hour workshop. So thank you, speaker, again.